So far, our discussion of continuity has been on a point-by-point basis. So we said that if you can get from one point on a function to points with x values immediately adjacent to it without having to lift your pencil off the paper, then the function is continuous at that point. So for example, this function here is continuous at all points in this interior because you can get from any of those points to points with x values immediately adjacent to it without lifting your pencil off the paper. But what does it mean for an entire function to be continuous? Well, depending on who you ask, it can mean one of two things. So the first possible meaning is that the function is continuous for the set of all real numbers. So this function here, which is continuous everywhere in its domain, but whose domain is only the open interval from c to d, this function would not be deemed continuous under this definition because it's not defined outside of this interval. So for most of the set of real numbers, it's not defined, and it certainly cannot be continuous where it's not defined. But the second definition of continuity of a function that you'll run across is that the function is continuous at all points in its domain of definition. So this function is defined over the open interval c to d, and it is actually continuous at all points in this interval. So under this second definition of continuity, this function would be deemed a continuous function, while it would not under this first definition. But this second definition does actually pose some problems. I'm going to show you an example to illustrate why. So here we have a function that can be thought of as defined over the open interval c to d. And if we think of it being defined over the open interval c to d, then it's discontinuous at, let's say, this point A where the hole is inside that open interval. So it is not continuous at all points in its domain of definition. But because this function is actually not defined at A, we could also say that it's defined over these two subintervals. So the open interval c to d, as well as, and this is just or c to a, excuse me. So this should be an a, c to a, the open interval c to a, and this is just a u, means the union of two intervals. So as well as the open interval a to d. So this, if we understand that it's not defined at A, well then it's continuous at every point in this open interval c to a, right? Because we can draw the function without having to lift our pencil off the paper. It's also continuous at every point in this open interval a to d. So if we consider the union of these two open intervals as its domain of definition, then we would say it is actually continuous everywhere in its domain of definition. But if we considered its domain of definition to be this larger open interval c to d, you could see that it's discontinuous at A, and that would be within its domain of definition if we say the domain of definition is this open interval c to d. And it would not be deemed a continuous function because A is a point where in its domain of definition where it is discontinuous. So to make things very clear, the examples will specifically ask about a function's continuity at a specific point over a particular interval or over the set of all real numbers. In the next video, we'll go over more examples of determining where functions are continuous.